Okay, we're going to do the second half of lesson 31, which is unit 6-1, page 343. What we've not done is talked about arc length in the area of a sector, but before we do that, we're going to review, we're going to recreate our memory work now that we know about radians, and then we're going to do some random practice so that we know how to use this information, okay? First of all, 0 degrees is 0 radians. That's going to be kind of obvious. Let things reconnect here. I'm not sure why they didn't. Give me just a second. We're temporarily experiencing difficulties. All right, hopefully this will work. 0 degrees is 0 radians. Now, from memory, we hope. Thank you, just said it there. That's good. What is the cosine of 0? Now, the reason we know, see, cosine is what, leg adjacent? So there's a value 1 if we actually went out there, right? With a radius of 1, so cosine of 0 is 1. What is the sine of 0? 0. And what is the tangent of 0? 0. Now, you've got a chart you can look at, but you realize on the next test that chart's in your head or you're in trouble. All right. Now, 30 degrees. How do we change to radians? We could divide by 180 and put the result over pi. How many times will 30 go into 180? 6. And so it's going to be pi over 6. That's how we do it quickly. Now let's do it slow motion. We started with degrees. We want to lose the name degrees, and we want to gain the name radians. We know that pi radians is 180 degrees. So we say, how many times will 30 go into 180? 6, and we end up with pi over that. You see how we did that quicker in our head? 30 goes into 186, so it's pi over 6. And so from now on, we know that anything on the unit circle that has a denominator of 6 has a reference angle of 30. Whether it's pi over 6, whether it's 5 pi over 6, whether it's 7 pi over 6, the reference angle is 30, you see. Okay? So we learned about that. And so if we were in quadrant 1 and we really did have 30 degrees, or we really did have pi over 6, then we know that the cosine of 30, or pi over 6, is square root 3 over 2, which needs to be committed to permanent memory. And the sine of 30, or pi over 6, is 1/2. And the tangent of 30, or pi over 6, is square root 3 over 3. Now, the tangent 60 square root 3, tangent 30 square root 3 over 3. The divided by 3 makes it smaller, which makes sense. It would go with the smaller angle, would have a smaller ratio, you see. Anyway, and then we've got 45 degrees. Now, how do we quickly think about what the denominator would need to be if we have 45 degrees? My denominator of my radian thing would be what? 180 divided by 45, which is 4. So it's going to be a pi over 4. 180 divided by 45 is 4. That means every time we see a denominator of 4, we're thinking about a reference angle of 45 degrees, which we should have memorized. What is the cosine of 45? Square root 2 over 2. Sine 45, same, square root 2 over 2. Tangent 45, 1. Or we could say cosine pi over 4, which is the same as 45, is such and such. Okay? Everybody kind of got what we're doing. All right, 60. How can we quickly find the denominator that goes with pi over something for 60 degrees? Well, same way. 180 divided by 60. What's 180 divided by 60? 3. And so we're going to have pi over 3. 60 goes into 183. That tells us then that every time we see a denominator of 3, whether it's pi over 3, whether it's 2 pi over 3, 4 pi over 3, 5 pi over 3, 7 pi over 3, you're going to have a 60-degree reference angle. Okay? The bigger it is, it changes quadrants, you know. And then when it changes quadrants, we got to come back over here and think, is it positive or negative when we moved into that other quadrant? We'll deal with that in a minute. We're still in quadrant 1 here. Okay, now, how would we get the denominator then that goes with a 90-degree angle? Well, you'd divide by 180 again. So 180 divided by 90 is 2. And so 90 is the same as pi over 2. And so let's go back to our 60. We didn't fill it in. What is the cosine of 60? Sine of 60 and tangent 60. And we hope that those are memorized just like that. Fast as we can say them, they're in there. Okay? Okay, 90 degrees. What is the cosine of 90? 0. What is the sine of 90? 1. What is the tangent of 90? Undefined, because you would have a division by 0 error. If you put your tangent, which is y over x, x is 0, you'd have a division by 0 error. If you went back to our original creating this stuff. Okay, that was the 90. Now what about 180? What's 180 in terms of pi as a radians? Pi, that was our conversion. I'm getting off a little. I'm going to shift this up. 180 is pi. 90 is pi over 2. The 180 in pi was that's what we built all this on, right? Now, 180, what happens when we go from sine of 0 over to sine of 90, or cosine of 0 over to cosine of 90? What happens when we go from over here to over here? It's a sign change, right? So it's a sign change. So if we go to the 0 in 180, there's going to be a sign change. Cosine was 1 on 0, so what's it going to be on 180? Negative 1. Sine was 0, so we're going to get a negative 0, which is still 0. And tangent was 0, so we're going to get a negative 0, which is still 0. When you go from 0 to 180, there's a sign change. When you go from 90 up here to 270, there's a sign change, right? So when we want the 270, we just change the sign of 90. What was the cosine of 90? 0. And so we're going to have a negative of 0, which is 0. We'll get the radians there in a second. The sine of 90 was 1, so it's going to be the opposite sign of that negative 1. And negative undefined is still undefined. What is a radian measure that goes with 270 degrees? Okay, let's think about that. That much is pi over 2. On over to here is another pi over 2, which is 2 pi over 2, which is really pi. But it's the same as 2 pi over 2. 1 second. It's the same as 2 pi. Okay, so the 90 was pi over 2. 180 is 2 pi over 2, which is pi. And then if we go another one, that's 3 pi over 2 for 270. And if we went all the way over here, it would be 4 pi over 2. But that's 2 pi, which is a circle, right? Okay? Now, those of us who are not real good at fractions need to begin to get good at fractions, because you've got to think fractions and where they're at in your head. And your calculator's not going to help you, especially if you can't use a calculator on the test. So if I say 7 pi over 6, you've got to figure out where that's at, which means you got to think fractions to do it, okay? Does everybody see how we got the left side? Okay, so this was 3 pi over 2. Let me write it in there. Now what we're going to do is some random stuff just to show you how you're going to have to be able to use it. So I'm just going to make some up, and we're going to figure out how to deal with it. Let's say we had in radians, 3 pi over 4. So now your brains have to, I need to know what your brain is going to think, because you're not going to have a calculator or notes. What's the first thing your brain's going to think? Divided by 4. What's my reference angle? 45. And then what do you need to think? What quadrant? Fourth. If I went to pi, how many fourths would that be? 4 fourths. If I was at pi over 2, which is 90, how many fourths would that be? 2 fourths is a half, right? So I'm thinking, okay, 90 is pi over 2, 180 is pi, my denominator is 4, I need to be thinking in fourths. Pi over 2 is 2 fourths, pi is 4 fourths, I've got 3 fourths, I'm somewhere between 2 fourths and 3 fourths, and so I'm in quadrant 2. Now, if my reference angle is 45 degrees, then what does that mean? It means that my terminal side is 45 degrees away from the x-axis. And so 3 pi over 4 is here. It's somewhere between 2 pi over 4 and 4 pi over 4. And since my reference angle is 45, it means I'm 45 degrees before I hit the x-axis again. And I'm in quadrant 2. Now let's talk about all the little things. What is the cosine of 45 degrees? Square root 2 over 2. Is cosine positive or negative in quadrant 2? Well, the only thing that's positive in quadrant 2 is sine. Therefore, the answer to cosine is negative, square root 2 over 2. Okay? What is the sine of 45? Square root 2 over 2. Is sine positive or negative in quadrant 2? Positive, so that one's positive. What is the tangent of 45? 1. Is tangent positive or negative in quadrant 2? Negative, so that's negative 1. Okay? We'll do some more, because you're getting it. Y'all are doing really good. Some of you are getting sleepy. You probably really ought to wake up, because this is pretty important stuff. We're doing good, though. It's just a matter of doing our memory work. We got to make sure you understand it. That's what I'm trying to do. The memory work is on your own. The understanding it is my job to help you do that. Let's say that we had 5 pi. No, let's make it bigger. Let's do 11 pi over 6. 11 pi over 6. Okay. First thing we're going to think is what? What's the reference angle? My denominator is 6. Therefore, my reference angle is 30 degrees. Very good. Because 180 divided by 6 is 30. And then we need to think. What quadrant am I in? What quadrant am I in? Now, I'm dealing with 6. This is pi. How many 6 makes a whole? 6. How many 6 makes a half? How many 6 makes 1 1/2? 9. How many 6 makes 2 wholes? So we're thinking in terms of 6. See what we got to do? Okay. Now, where is 11 pi over 6? It's in quadrant 4. And it is 30 degrees away from 360. So that's the terminal side. It actually started way over here. See, my angle went all the way around. But its reference angle is 30 in quadrant 4. Okay, so what is the cosine of 30 degrees? Square root 3 over 2. I'm in quadrant 4, A, smart, trig, class. Cosine is positive, so it stays positive. What's the sine of 30? 1/2. In quadrant 4, sine is negative. What's the tangent of 30? Square 3 over 3. And in quadrant 4, tangent is negative. That's probably enough of them. You get the point that we're trying to make. So we think, what's the reference angle? What quadrant am I in? You're gonna have to know that we've got pi over 2, but we're going to write it in terms of that denominator. We have pi, but we need to write it in terms of that denominator. We've got 3 pi over 2, but we need to write it in terms of that denominator. We have 2 pi, but we need to write it in terms of that denominator, and then we can think about where it ends up, what quadrant. Once we figure out what quadrant, that simply tells us our positives and negatives. Okay? Any questions on that? Okay, now the other part of this lesson is arc lengths and areas of sectors. Arc lengths and areas of sectors. So, we're going to talk about arc length. Now, in your pre-calculus book, on page 345, it actually called it a circular arc. It called it a circular arc. I call it arc length because that's what we do in geometry. I'm an old geometry guy. Okay? Now, what I'm going to show you is the geometry way to do it and the pre-calculus way to do it. Those sleepy, wake up. I don't want to call your name out on a video. Anyway, thank you. Now, we're going to look at the geometry version. And we're going to look at the pre-calculus version. Now, first of all, a circle is the set of all points in a plane, a given distance from a given point in that plane. The given point is called the center, and the given distance is called the radius. The circumference of a circle, which is the distance around the circle, is 2 times pi times the radius. An arc length is a part of a circle. So an arc length, or a circular arc, is a part of the circumference. Also in geometry, you learned that a central angle is an angle whose sides are radii of the circle and whose vertex is the center of the circle. That is called a central angle. You learned that a central angle is equal to the measure of its intercepted arc. A central angle is equal to the measure of its intercepted arc. You learned all kinds of other stuff. An angle formed by a secant and a tangent to a circle from a point outside a circle is equal to 1/2 the difference in the intercepted arcs. Or an angle formed by 2 chords in a circle is 1/2 of the sum of the intercepted arcs. There's a bunch of stuff about that in geometry. But anyway, here our arc is equal to our angle. Now, let's just say that we had a circle with a radius of 4, and we wanted to find the length of this arc, and that angle is 30 degrees. Now, from geometry, how would we find, let's just call this AB. How would we find the length of arc AB in geometry? Well, what's the formula for circumference? I'm leaving some space here. 2 times pi times radius. That gives us the whole circle. How much of the circle do we have? We have 30 360ths of it. So in geometry we said, well, we have a fraction of the circumference. A fraction of the circumference. And then we solved that. And so we just stuck that in the calculator, and we had arc AB is equal to 1/3 of 8, so we'd have 8 pi over 3. 3 goes into 30, it goes 3/3, sorry, forget that. 3 goes into 36 12 times, doesn't it? So we'd have a 12 on the bottom, and 8/12 is 2/3, so 2 pi over 3. That would be the length in terms of pi, okay? That's the length of the arc in terms of pi. Now, let me show you just something. What if we wrote a formula? The length of the arc is equal to the degree over 360 times 2 times pi times radius. You see that? You understand that's the formula? Degree over 360 times 2 times pi times radius. What if I wanted to change that to radians? What would I do? Watch what happens to my formula. If I want to change to radians, I need to lose the name degrees. Ooh, that was not going to be pretty. Just a second. I want to put arc here. Instead of degrees, because this is really my degrees on the bottom. I want to change from 360 degrees into radians. If I was going to do that, I would need to lose the name degrees and gain the name radian. See that? If I was going to change that 360 part of that story, that formula that we had, into radians, I would want to lose the name degrees and gain the name radians. And I'm going to put my times 2 times pi times radius back in there. My 2 pi r back in there. So all I did is I inserted into my formula pi 180 over pi to convert my degrees into radians. Okay? Now look what's going to happen. Arc times the radius. Now my arc is my angle measure. If this was my angle and we called that theta, then what I would have is r theta. And so our formula for pre-calculus is arc length, which we call S, is equal to r theta. You see how we got it? By taking our geometry knowledge and converting the 360 degrees into radians. And it all canceled out, and we ended up with the arc length S is equal to r theta. So since we were going to deal with radians in pre-calculus, we don't use the geometry side, we use the pre-calculus side. Arc length is r theta. Okay, so now we're going to do the same problem over here. We've got a circle with a radius of 4, and we've got an angle measure that's 30 degrees, and we want to find this arc length AB. Now, theta here is going to be measured in radians. That's important. So what would the first thing we need to do here be? Change degrees to radians. So we're going to take that 30 degrees. We're going to lose the name degree, and we're going to gain the name radian. We're going to get pi over 6. In radians. And then to find my arc length, I just take radius times theta. Radius 4 times theta in radians, and I get 2 pi over 3, which was the exact same thing I got when I did all that geometry stuff. So we took our geometry formula in degrees, just inserted a conversion to radians, and came up with a formula for radians, which is a whole lot simpler than the formula for degrees. Now, we're in calculus, pre-calculus class, so what formula are we going to be using? S equal r theta. Now, do you have to the rest of your life remember how we converted this formula over? No, you could forget that and never think about it again. But I wanted to show that to folks who might have a good geometry background so you can understand. Was that important to us today? Yes, because we do need to know how to go from degrees to radians and use it in an application. We used it in a formula to create a new formula in terms of radians instead of degrees. But that's not today's lesson. Today's lesson is just plug into this and solve. Okay? So let's do the let's do the problems off of the worksheet that have to do with that now, and then we'll go and we'll do our area the same way. Okay? So I'm going to get rid of some stuff here. And we are on question number 7 on our worksheet, question number 7. Now, question 7 says, given the measure of a central angle, find the length of its intercepted arc in a circle of radius 14. Well, we're looking for the arc length, and we know arc length is called S, and S is equal to radius times theta, where theta is measured in radians. It gave you theta in radians. So all you have to do is say arc length is equal to radius, which is 14, times theta in radians, which was given 5 pi over 12, and solve. And you're done. If you wrote it as a fraction, you could say 2 goes into 12 6 times, 2 goes into 14 7 times. 7 times 5 is 35 pi over 6. That's the exact answer. It did say, though, round to the nearest tenth. So what you're going to do is plug that in the calculator. 35 pi, divide 6, and get a decimal. We're going to leave it. The question was, somebody's paying attention. That's good. The question was, what are we going to do on the test if the test says you can't use the calculator? That means on the test you would leave it in its exact form, right? Instead of writing it as a decimal in simplest form, right? Good, you were paying attention. That's good. But it's 18.3 if you write it as a decimal in simplest form. Good. So if I don't let you use the calculator on a test, you're obviously going to leave it written as in terms of pi, 35 pi over 6. Right. You still can do this test without a calculator, methinks. Any questions on that? All right, so if you don't have a calculator, we won't be rounding to the nearest tenth. We will be writing them in terms of pi. Any questions on number 7? Number 8. Number 8, we have 282 degrees. We know that our arc length is r theta. But it gave us our theta in degrees, and so we need to convert. So we're going to have to take the 282 degrees, and we're going to convert it into radians. We're going to lose the name degree and gain the name radian. We'll cross-reduce as we can. 2 will go into that 90. 2 will go into that 141. And so in radians, it's 141 pi over 90. So now I have my theta in radians. My arc length is going to be r. My radius, which is 14, times my theta in terms of radians, which is 141 pi over 90. 2 goes into 14, 7. 2 goes into 90, 45. And so we're going to get 700 to 8987. See, we didn't need a calculator. Over 45, but I probably messed up since I just said that. 987 pi over 45, we hope. 7 to 80, 987 pi over 45. Good. So there's the exact answer. You plug that in the calculator, you get, what, 68.9? Rounded to the nearest tenth. All right, any questions on 7 and 8? I could have just said arc length S equal R theta, but I wanted you to see the geometry connection and how we derive that using our conversion from degrees to radians. These formulas didn't just come out of the air. They were created with a little bit of geometry and a little bit of trigonometry. All right, let's talk about area of a sector. Now, a sector, if you're talking about the area of a sector, you're talking about the area of that whole chunk, like a piece of the area of a circle, kind of like the area of a slice of pizza. And we know that the formula for area of a circle is pi times the radius square, right? And so if we were talking about a sector, let's just say that we had a circle with a radius of 4, and we had an angle of 30 degrees, and we wanted the area of that slice of pizza, then what we would do is we would put our arc 30 over 360 times the area formula, right? So we would get area equal 30 over 360 times pi times my radius of 4 square. And we would have a 12th and a 16. 16 over 12 would be 4 pi over 3, correct? Yeah. 30 over 360 is going to give me a 12 on the bottom for the 360. 4 squared 16, so you're going to have a 16 over 12. 4 goes into 16, 4. 4 goes into 12, 3. 4 pi over 3 simplified. Now, let's manipulate our area formula. Remember that area is the arc, or theta, divided by 360 times pi times radius squared. I left a gap because I'm going to convert. But we can see that my arc, my area of my sector is a fraction of the area formula pi r squared. But I need to change the denominator of 360 degrees. I need to change it into radians. And so I'm going to insert a conversion, which is going to be lose the name degrees and gain the name radians. And then I'm going to go through that cancellation. 180 goes into 362. Pi cancels pi. What do I get? 1/2 theta r squared. So the pre-calculus version for the formula for the area of a sector is equal to 1/2 theta r squared, or theta r squared over 2, or theta over 2 r squared. Okay? In the textbook, it gave us which one of those versions. I didn't even look. I should have looked probably. 1/2 r squared theta. So they put it like this in the book. They put area is equal to 1/2 r squared theta. Okay? They put the r squared first. 1/2 r squared theta. You see how we quickly, with our conversion from degrees to radians, changed our geometry formula to a pre-calculus formula? Okay? And then we're just going to use that. I'm not going to go back and do this problem again. We're just going to look at the ones on the review here. So there's our formula. Area is 1/2 r squared theta. And we're going to do number 9. So number 9, using the formula area equal 1/2 r squared theta, it gave us that we have a radius of, it didn't say, did it? 10. Oh, it didn't say, but it's down here. I gave you the radius of the circle, so number 9. gives us theta, and its theta is equal to 5 pi over 12, and it gave us a radius of 10. Theta is supposed to be a little taller than that, and skinny guy like this, something like that. And so we're going to have area is equal to 1/2 times the radius of 10 square times theta, which is 5 pi over 12. 1/2 r square theta. This is going to turn into 100 right here, correct? And then we can start reducing. 2 goes into 2 once, 2 goes into 150 times. 2 will go into 12 6 times. 2 will go into 50 25 times. We'll have 25 times 5, which is 125 pi over 6. 125 pi over 6 is the exact answer. If you were to divide that out, you would get an approximated answer rounded to the nearest tenth of 65.4. Any questions on that? So if we're going to do exact answers, obviously without a calculator, we'll want exact answers, and we'll do all that cross multiplying. If you need to get a little over on the side with a pencil and scratch out some multiplication and do that. Okay? Yes. I said this 2 goes into that 150, and then I took a 2 out of that 12 and got a 6, and then I took a 2 out of that 50. I just kept cross-reducing until I got it as small as I could. Right. Any questions on number 9? Everybody good? Number 10. Number 10, we want the area of the sector, which again is like a slice of pizza. We've got theta is equal to pi over 8, and we have a circle with a radius of 7. You understand this is what we have, circle with radius 7. My angle is pi over 8. Pi over 4 is 45, so it's half of 45, which is 22.5 degrees. It'd be something like that. You're going to want the area of that slice of pizza. Remember, pi over 4 was 45, so pi over 8 is half of 45, so the angle is 22.5 degrees if we were going to do it in degrees, which we aren't, but that gives you a little bit of a picture there. And so we're going to have area is equal to 1/2 r square theta, 1/2 r square theta. And so we're going to have area is equal to 1/2 of the radius, which is 7 square, times theta, which is pi over 8. And so we get area equal 7 squared is 49. It goes on top with the pi. On bottom, we've got a 2 and an 8, which would be a 16. So we'd have 49 pi over 16 once we do the multiplication. That's the exact answer. And then 49 pi over 16, excuse me, I said 18, comes out to be rounded to the nearest tenth of 9.6. Any questions on finding arc lengths and areas of sectors? So arc length S is equal to r theta. Area of a sector is 1/2 r square theta. And then we've got all that memory work we have to do. On this test, you're not going to use a calculator or notes. You're going to have to do all of those unit circle things from your head. All right, appreciate your attention.